Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my great pleasure to welcome Tom Restenbart. Tom is a PhD candidate from UCSD, and his advisor is Mihir Balar, a very famous cryptographer. And he also collaborated extensively with Stefan Savage, Yushi Kono, and all those folks that we are very familiar with. So Tom is interviewing jointly with the Security and Privacy Research Group and the Crypto Research Group. He's interviewing for both researchers and postdocs position. And Tom is going to talk about his dissertation work on how he has improved the interface between systems and cryptography.
Well, thank you very much for that kind introduction. So it's great to be up here in Redmond, talk about my work in computer security. And so the background, of course, for work in computer security is that it's incredibly hard to get our complex computing technologies of today to be secure in the face of malicious users. And of course, the consequence of having insecurity, as we well know, can be quite drastic, whether it's criminals breaking into corporate or other organizations' data centers and making off with data on hundreds of millions of credit card accounts, or growing privacy concerns regarding the fact that we're carrying smartphones with us all over the place, and these are notifying third parties of our locations. Or even some of my recent work highlights how new technologies, in this case cloud computing, can really give rise to interesting new threats that we need to consider. And so to handle all of these, to help us in building more secure systems, we really like to have powerful tools. And one such is cryptography. This allows, for example, encrypting a message so that can be sent securely and privately over an insecure public network. And the reason that cryptography is so powerful is not necessarily what we set out to do, so much as how we verify that we've accomplished our goal. And here, what cryptographers do is make use of a framework known as provable security. So the idea is that a cryptographer sits down and defines precisely and mathematically the algorithms involved, the security goals, so what the tools are supposed to be accomplishing, and quantifying the adversarial resources that they expect attackers to have, whether this be running time or access to other information. And then now relative to this abstract model, what a cryptographer does is give a proof of security, an MP-complete style reduction, showing that any attacker who can break a cryptographic scheme, well, this implies the ability to break some underlying simpler primitive. And what this reduction does is actually gives us a very strong guarantee of security if we make a judicious choice of our underlying primitive, for example, basing it on factoring large composite numbers or some very thoroughly studied primitive, such as the AES block cipher. So in the end, we get a very strong validation tool. We can use proofs to understand that attackers, at least if they're working within this abstract model that we've designed, really have very little chance of breaking the cryptographic mechanisms. So what's the catch? Well, the problem is really in the handoff, right? Because on one hand, we have systems with real implementations of cryptographic protocols and real threats. And on the other hand, we have cryptographers and using abstract models to design and verify their algorithms. And so the problem is if there's any mismatches between these two worlds, then these mismatches can be found and exploited by attackers. So to get back to some of those examples on the first slide, right, we have problems like breaking into databases. And here, the cryptographic tools that we have just aren't deployable due to legacy constraints. And so this leaves plain text vulnerable. Location privacy really isn't achievable by cryptography alone. Of course, you have other systems-related phenomena like the fact that we're using the internet, and this reveals our location already to third parties. And then there's more subtle issues about using cryptography in new environments that were not envisioned by designers and where implicit security-critical assumptions end up being invalidated. So my work over the last bunch of years has really been about trying to tackle these problems that occur at the intersection of cryptography and systems. understanding the types of gaps between models and reality, how these types of gaps can be exploited by attackers, and then, of course, trying to figure out ways to improve the situation and fix the problems. And so, consequently, I've taken a pretty broad a view of research, working both on understanding threats. So really, this is just a nice way of saying finding attacks against systems that are using cryptography. Also building systems, so starting from scratch to create a system that uses cryptography in some broader system security context. And then also working on improving the cryptographic theory and tools that we have in order to make them more useful for practical situations. So what I'm going to do in this talk is basically go over a bunch of different projects at a pretty high level and relatively quickly. I'll talk about this issue of encrypting credit card numbers in databases, problems related to the use of randomness in cryptographic protocols. I'll look at building a security system in the context of device tracking. And then I'll talk about my most recent work at the end in the context of cloud computing and revealing new threats there. So let me say, since I'm going to be going over things relatively quickly and kind of high level, I'd encourage you to jump up and ask questions or interrupt at any time. We can make this quite interactive. Be good. OK, so let me start off by talking about this problem with credit card numbers. And the fact is that we just have millions of databases out there that are storing account information about people. And these databases, so they're storing names and also credit card numbers, for example. And the fact is, if we wanted to encrypt these credit card numbers so that if an attacker does succeed in breaking into a system, that now he would only have access to ciphertext as opposed to the plain text credit card number data. Well, the fact is that our existing traditional cryptographic tools just aren't going to help us with the job very well. And this is for a relatively simple reason. Say we want to use something like AES, a traditional block cipher. It's a map that uses a key to encrypt a plain text of 128 bits to a ciphertext of 128 bits. And so if we use this to encrypt a credit card number, well, the result is that we get a ciphertext that is 128 bits. And there's no way to encode 128 bits into a 16 decimal digit number. And so literally the ciphertext just can't fit back into the database in lieu of where the plain text was.
What about a stream cipher?
You can use a stream cipher, but it won't give you much security. So I'll talk about that in part in a minute. So the problem is, so this is a kind of a gap, right? Our cryptographic tools, stream ciphers, block ciphers, these things don't really solve the task at hand. And so in practice, we don't end up using encryption in databases as much as we might like. And so the result is that when criminals break into companies like TJ Maxx or even credit card processing systems like Heartland Payment Systems, they end up making off with quite a bit of data. So we'd like to fix this situation.
So this is a particular database schema somehow is used by all these people, and that just did not work out.
No, I was giving you a specific example, but the point is that there's a lot of software and database systems that are built around the idea that you have a 16 or 18-digit credit card number, and to use the existing cryptographic mechanisms that are actually secure for this setting, then you would have to redesign the database and the software around that cryptographic mechanism, because you can't just replace in place the credit card number with a ciphertext. And so
This assumes the method of entry for stealing this data can be solved with encryption. If the vast majority of the data is stolen via social engineering or trust or bribes, then encryption is no better than having a machine with no encryption at all. True.
That's partly true. The point is that we would like to use encryption in this setting to narrow and limit the focus of what we need to protect, right? So you're moving from having to protect a database or multiple copies of a database in various places on various systems to having to protect the cryptographic key, right? And
examples of stolen data be solved with encryption?
Yeah, that's the idea. And I'll talk about how that happens to a certain extent. We can talk about details later in a minute. So the suggestion actually for
explain why the stream cipher would have been insecure.
Right. So the problem is that if you use a stream cipher, right, you have to you're going to encrypt with like a pad basically, right? And so if you use the same pad for multiple plaintext, so where do you store the salts, right? Is the question.
The salt is you've got other information in those fields.
why not use those as the salts?
Well, the question becomes then you have to ensure that all the information is unique in every single field in the database. And so this becomes a usability issue for the...
Row ID is presumably one of the things you can solve with, right?
Right. So
almost any database is going to have a unique ID for each entry that's stored there, so that you can...
Yeah, so this is, these are all great questions. And I think the fact is I don't know all the details about the deployment requirements in these settings. But when we talk to people in industry who are deploying or wanting to deploy credit card encryption mechanisms, they find that there's too many constraints to use things like stream ciphers. And so what they really want is a standalone solution that you basically handed a credit card number, and under some particular key that's easy to store in a hardware security module, you get back a credit card number that you can then place into the database. And the way it's actually ended up being deployed is that they actually take the credit card numbers when they first enter a network, for example, and send it off to HSM right away and get back a credit card number even before it ends up landing in a database. So this provides global security no matter where the credit card information ends up appearing, not just in the database, but throughout the whole network. Okay, so the solution that I've basically just kind of highlighted a little bit is this idea that we want to have what's called format-preserving encryption. And the idea is that we want to have encryption mechanisms that can take, for example, a valid credit card number and map it under a key now to a ciphertext that is also a valid credit card number. Okay, and this replies, for this particular example, in-place replacement of the plain text with a ciphertext. And the surrounding systems that also use this credit card number now can just treat the ciphertext as before. So how can we build such a format-preserving encryption scheme? Well, we could, of course, use AES and then just truncate the output. But this isn't going to work, right? You've thrown away some of the values you need to decrypt the ciphertext. Okay, we can also, of course, use something like electronic codebook mode. This actually does allow format preservation. And for example, what this would do is associate to each plaintext digit encryption of it, right? So this key is the table now. And so to encrypt a credit card number, we just replace literally 2 with the 7 and 3 with 4, etc.
That would be the same as the unsalted stream cipher problem.
Exactly. This is the same as the unsalted stream cipher problem, right? So yeah, of course, this isn't secure, right? Because as soon as you have one plaintext ciphertext pair, you learn the codebook. Okay, I'm talking to too expert of an audience. Non-cryptographers love this example. So anyway, this is a horrible idea from a security standpoint, right? It's the same as the unsalted stream cipher. I'm sorry. What's that? Well, this is. I could go through lots of different attempts. We could spend all day talking about bad ideas. Okay, so yeah, these things are bad straw mans, right? So what we really want, okay, so we want a format-preserving encryption scheme for credit card numbers. But then when we came and looked at this problem, we said, well, why are we restricting our attention to credit card numbers? We may also want to encrypt, say, a valid postal address back to a ciphertext that's also chosen from the space of valid postal addresses for some subset of all postal addresses. Or maybe we want to apply this to some formatted medical record and get a ciphertext back that is also a medical record. And so what we said is, well, actually, maybe we should actually try and target a more general tool, right? Providing an encryption mechanism that actually can preserve membership in, say, any arbitrary regular language. And this is actually the problem that we set out to solve and did solve. So let me just tell you a bit at a high level about what we did. We provided the first formal modern cryptographic treatment of the format-preserving encryption problem. So this means defining what it means to have a scheme, providing security notions, for example, resistance to message recovery attacks. We don't want people from a ciphertext to be able to recover the credit card number or other information. And then we provide practical constructions. But doing this formalization actually allowed us to take advantage of quite a bit of cryptographic theory and also theory related to, for example, ranking of regular languages. And so just to give a flavor of what the proposed solution looks like, at least for the specific case of credit card numbers, not for an arbitrary regular language, but for credit cards, well, we end up using a modified variant of Luger-Rakoff or Feistel networks. And so the idea is you take a 16-digit credit card, split it into 2 sides, and run the right half through AES, and now you have a 128-bit value that you can encode as a number, and you add this mod 10 to the 8th with the left-hand side, and you get the right half output, and you just drop down the right-hand side to the left-hand side. And the point is this round now is invertible, so we can go backwards through this. And then we can do many rounds of this to achieve security and provable security, so that we can show that for any adversary A, for example, that's trying to break our scheme in terms of, say, message recovery, well, then this is actually going to imply the ability to break AS in some non-trivial way. And so the contrapositive gives us a nice guarantee of security that the format-preserving encryption scheme is as secure as AES. And this means that we haven't introduced any problems in the development of the FPE scheme.
Are there any boundary cases or like odd length sequences that you need to encrypt?
Right. So in the general case, right, you have to deal with this underlying problem of encrypting on any arbitrary finite set. And so, for example, if you have a prime ordered set, then this becomes problematic. And so there's a bunch of techniques that I didn't talk about to deal with this. But for that particular case, you end up using a actually relatively old technique called cycle walking. Actually, it dates back to like the 1910s or something in World War I. But the idea is you can iterate a cipher that works on a slightly larger domain to get back into a prime order set, with one that can be split evenly in half, for example. Mm-hmm.
Do you have to know something about the distribution of plain text?
Yes. Well, yes and no. So the definitions in the scheme don't require any knowledge of the distribution of plain text. Of course, if there's only one plain text and you get a deterministic encryption of that one plain text, you know that there's one plain text. So if in general, if there's very low entropy in terms of the plain text size, and you see lots of examples, there could be concern that you are learning information about partial information about messages. But in these, we still have a security win here because we're still encrypting it. So you would have to have access to an encryption box to actually check to see. So say you have some relatively small set of potential plain text that you know occurred. You'd still need to do trial encryptions with the box to actually check if the ciphertext matches the one you have in hand. And so this can be handled by, for example, metering the number of encryptions allowed, per second or something. And it's a concern, but it's.
If you steal the whole database, can't you just say, oh well, the one that appears most, that's California, and the one that appears next most, that's New York?
Oh, I see what you're saying. Yeah. So in deployments, we of course suggest using salts as well. So these are actually tweakable encryption schemes, what they call it technically. So what you can do is not only put the message and encrypt under a key, but you can actually, in some settings, you can salt via the other elements. And so that is an important way to important help to deal with that type of variation issue. Mm-hmm. But it's fundamental in this case that if you need deterministic encryption, which is what we need here to achieve this legacy compatibility that the industry people are asking for, then you have this concern about small message spaces. So this work, we were talking to people from various companies when we were working on this, and the result is that there's a standard that's been proposed to NIST based on this work. And in fact, some of these companies are actually already deploying this technology. So Heartland Payment Systems is one of the companies saw that had problems before, and they are prototyping a system based on FPE being offered by Voltage. So they actually do like this functionality. Okay, so that was an example of a kind of mismatch between cryptography and systems that was at least simple to state, right? We just didn't have the right types of tools to, yeah.
Well, just one thing before you move on. I'm not sure this is the appropriate place for it, but when you say this is sort of the first modern attempt at this sort of thing, are you intentionally dismissing Schroepel's hasty pudding approach?
Oh, yeah. So, well, he didn't formalize format-preserving encryption, right? He formalized having a arbitrary bit-oriented cipher, right? And he did it by hand. So the problem with hasty pudding is, so it gives you something that works on bit strings of arbitrary size, but not something that works on arbitrary formats. And so there is an extra step to actually.
I think it worked on arbitrary formats, but it was very cumbersome.
That's
He described it as an omnicipher that could encrypt it any form and put it back in exactly that form with no extra space.
So he didn't talk about doing things like encrypting regular languages, I think, at all. So he does. It's a very flexible cipher. It's true, and we cite the work extensively, of course. The basically recognized problem with hasty pudding is no one looked at it in terms of security. So no one knows if it's secure because it was designed by hand. Whereas with these types of schemes, you can take advantage of the analysis of AES that's been going on for the last 10 years and is ongoing. Okay, so let me move on to talk about a second problem, which is the use of randomization in cryptographic algorithms and how this causes problems in practical settings. So just as a bit of background, we have modern public key encryption schemes is a good example that I'll keep coming back to. And this allows generating a public key secret key pair and distributing the public key so others can encrypt messages so that only the person with the secret key can decrypt. But the point is that the goal now for modern public key encryption schemes is that they are randomized, which means that the encryption mechanism not only takes the message and the public key, but also takes a string of random bits, or bits that should be chosen uniformly at random from the set of all such bit strings. And the reason for this is that it provides a stronger security in some applications. So for example, if we're communicating between one party and another, and we have an adversary that's seeing some of the ciphertext going by, and the adversary can't even tell if the same message was encrypted twice. And so this can be important in certain contexts. So in theory, of course, we can just assume that we have access to some algorithm that samples this value R at random. But in practice, we have to implement this somehow. And so what's done typically is using a random number generator. So software-based random number generators, for example, measure certain unpredictable events like keyboard presses from the user or mouse movements, and then try to extract from these measurements a string R that should be uniform at random from an adversary's point of view. But the problem is, of course, that there's been a long line of work showing that random number generators are really hard to get right. So this ends up with problems that R is exposed to attackers or repeated or even predictable in the worst case. So there's this famous example, at least in this community, it should be pretty well known, about the Debian OpenSSL bug where they commented out a couple lines of code in the source base, and these were the lines of code that were actually responsible for adding measurements to the random number generator. And so you ended up with a very small set of possible R values that are predictable to an adversary's point of view.
So this is a problem not just for randomness in protocols, but keys are generally from the same source, right? So
this is true. So yeah, of course, if you have keys that are generated with bad randomness, your host. I mean, I think there's a distinction here between, and then one that's important here is that, between frequent and infrequent operations. So if you're generating a key, you kind of generate the public key secret key pair once for a long time, but then every time you encrypt a new message, you need new randomness constantly. And so it seems intrinsically more difficult. I mean, you need more randomness to deal with the problem of generating randomness for message encryption, and you need it in a variety of contexts, whereas you can at least, in the ideal case, sit down with and generate the public key secret key pair once and then distribute the public key.
You can, but you're almost certainly using the same underlying random number generator. And so if it's got a small set of R,
right,
then not only are your protocol randomness broken, but so are your keys, and you're just completely screwed.
Yeah, and there's something fundamental there that we can't change crypto to make up for that problem, right? If you don't have any randomness anywhere, well, cryptography doesn't work. Absolutely. So to lead in a little bit, what I'm going to deal with is one of these two problems, which is dealing with the routine randomness. And if you have good keys, then we'll show that you can do something quite a bit better than what's currently done with bad routine randomness. Let me tell you about another place from my recent work where random number generators kind of fail. And this is in the context of virtual machines. And the idea is that security experts and companies are advertising the idea that you should do browsing within a virtual machine. And so the idea is pretty straightforward. So you set up a guest operating system and run, say, your Firefox or some other application within it. And then you can take, at this point, a clean snapshot of the virtual machine. What is this? It's a copy of the entire state, including active memory and persistent storage. And this snapshot, then, you can reset to every time you want to do a browsing session. Okay? So with the idea that now if in one browsing session you visit a bad site and you have a vulnerability exploited, well then the virtual machine ends up getting compromised, but the isolation guarantees the hypervisor should ensure that the host operating system remains virus-free. And so next time you go surf and you reset to your snapshot, then well, the malware's gone and you have a new secure session. So this has some very tangible security benefits, but some recent work we showed this actually causes problems for cryptographic protocols, and it's because of random number generation failures. So if you're in this setting and you reset to your virtual machine and then now visit a secure website, so use HTTPS, then what happens is the TLS client on the browser uses random number generator to generate some secret randomness. That's then encrypted and sent over to the server. And then this now shared secret is used to bootstrap a secure session to do your banking. Now the problem, of course, or maybe not of course, the problem that we found out is that if you then reset to this snapshot and visit a new website that's using HTTPS, you actually end up, the random number generator spits out the same values for the browser. And so you end up sending this secret value to the next server you visit. And this, of course, is a problem because this is all the secret data needed to decrypt a transcript of the banking session. This wasn't an abstract problem. This is a problem with real browsers. Firefox and Chrome had this behavior. And again, the problem is that the random number generation process is really being undermined by this snapshotting. And this isn't limited just to browsers. We also looked at TLS servers, and particularly we looked at Apache mod SSL. And there, if you're running it multiple times from the same snapshot, then you end up, and you're using DSA mode, then you can actually end up stealing the secret key from the server. And in general, we think that these what are the first examples of what we're calling VM reset vulnerabilities really seem to be a big, the tip of the iceberg, so to speak, in problems here, because there's a lot of legacy software that's being run in virtualized environments, and whether they deal with snapshotting correctly is an open question. But back to the story about cryptographic randomness. Well,
Can you propose a fix, or is it easy to fix?
So with that's actually so that we haven't worked on this. So this brings up two issues which I'll talk about in this slide, right? One is that we need to revisit the design of RNGs in these applications. So there seems like in the short term there could be a good fix, which is just that you don't have Firefox, for example, cache randomness up front, and it just does it every time you do a new HTTP REST request. Whether in all virtualized environments this is actually giving you good, new, different randomness each time you run from the snapshot is an open question and something we don't know. And we think actually fixing the problem in general is going to require more extensive changes. You're going to have to revisit hypervisor design, understand that the random number generators need to be backed up by something from the hypervisor, either hardware or software-based, and also have all your applications aware of the fact that they can't cache randomness for long periods of time, because this would still allow this type of reset problem.
Firefox having read while bug, it's application.
It's a good question. We notified the VMM designers as well, and they said it was a Firefox bug. But the
Call the VMM random number generator after taking the snapshot in two different instantiations, right? You take a snapshot, you instantiate it, call genram, and then you do the same thing again when you get.
Well, that would be true if you had a hypervisor that gave you a random number generator. In this case, it's not set up that way.
I mean, if you just use time, it would be fine, right?
No. Okay, so there's two things here. If you have a hypervisor that's providing a random number generator, so for example, you replace dev random with something that the VMM is supplying the randomness for, then you would be okay, I think. But this requires a change to some of the virtual machine hypervisor design. If you just call dev random and rely on the guest operating system to generate the randomness, well, the problem is dev random gets rolled back with the snapshot as well. And so it's not entirely clear that you are going to get good randomness.
That was the question.
Yeah.
But if you
No, it's an open question. I don't know, actually. I mean, it seems like it depends on a lot of things, right? What measurements they're taking, whether there's enough differential entropy between one run to the next run. And this is something we want to study and measure to understand. I mean, to conjecture, I think having software-based random number generators in this setting inside the guest OS only seems kind of like doomed to failure at some point. But whether it's actually a vulnerability or not is a question.
So can you always reliably reset the snapshot to the point after the initial whatever the randomness is cached in the Firefox? Or, I mean, so
the way it works is
if you go back before that's cached, then that's no problem,
right. Yes. Yeah.
So can you control?
So the way it worked with Firefox, for example, is that the random number generator is used at the time that Firefox is booted up. So if you snapshot at any point after Firefox is run, so in particular experiment, we loaded Firefox, let it sit for a second, took a snapshot, and then went back. And this is consistent behavior that the same randomness got taken all the time. If you took a snapshot in the middle of it booting up or something, then you get inconsistent behavior. But this is unlikely to happen from a usage point of view. So
a simple fix from the snapshot functionality of VMware could be you roll back your execution before you start the browser.
You can't really have a snapshot, right? Or
yeah,
snapshot process state.
Yeah, I don't know if there is I mean, one simple fix would be to have an architectural, like an Intel instruction that gave you randomness, and then maybe you'd be okay. But this is totally circumventing the hypervisor. I mean, only if you call it, right? So there's multiple layers of problems here, right? The applications need to be aware of the fact that they're being having snapshots taking of them. And the fact is that purposely the way hypervisors are designed is so that applications don't need to be aware of these things like snapshots, right? And that's a functionality thing. This is allowing legacy compatible deployment of systems in virtualized environments. So there's this tension between functionality and security here. And I think this is, as I was trying to say before, indicative of a broad set of issues there. I mean, we're taking all this legacy code, we're throwing in virtualized containers. There's fundamentally new things going on with these virtualized containers, right? We're rolling things back, we're resetting, we're making copies, duplicates, and launching them off. And this is only going to become a bigger problem. And so to have a complete system solution I think is an open question and something that I'm looking at. But I don't think there's really a quick fix that's sound in any principled sense.
I think there is a possibility. There's a pretty easy, from a systems perspective, I think there is one fairly easy trigger point, which is on these rollbacks that you force like an address change. That's something that these applications are used to dealing with. So
you still have to modify all the applications
right.
that could be vulnerable.
But at least there's a point where you can say, you don't have to introduce a new event. You just have to introduce the knowledge into developers that when you see the address change, you ought to go get a new random number seed as well.
So that's going to be a significant amount of work. So you're going to have to educate all the developers here at Microsoft on this, right? Yeah. So there's two things, right? I mean, basically, and this is funny because when I was talking to Chrome or Firefox, one of the guys, they were saying, like, well, look, we're using best practices for random number generation in our code, and so we should be fine. And I'm like, well, okay, the problem is with virtualization, we're going to have to really rethink best practices for random number generation usage. And I mean, that's just the fact, I think. So that's a whole host of issues that I'm not going to talk about. What I am going to talk about in the next few slides is this kind of somewhat embarrassing fact, maybe, that our cryptographic operations, in the face of using this repeat randomness, like fall over completely, right? Session keys get revealed, okay. Also, secret keys for DSA, signature scheme you can steal them from the server. And so our question the question that this work motivated in part was, can we make the cryptography more robust to these type of failures of routine randomness? So to reiterate, we have kind of varying levels of randomness, right? We have a proper RNG that's providing always fresh randomness. We have these settings like VM resets where you get repeat usage of randomness. Or you even have things like the Debian OpenSSL debacle, which you end up with a very set of predictable values being output. And with our traditional cryptographic mechanisms, basically they're designed in this context where you assume good randomness always, and so you get strong security guarantees given a good proper random number generator, but otherwise everything fails. And so our idea was like, okay, let's fix this situation. And we call this hedged cryptography. That we want our cryptographic operations, our routine cryptographic operations, to be as secure as possible given whatever randomness they're given. So for example, with public key encryption, when we get good randomness, we achieve our traditional strongest security goals. When we get, for example, repeat randomness given to our encryption algorithm, then we're not going to be able to, and provably so, meet our strongest security goals. But what we'll do is, instead of failing completely, we'll achieve some weaker but still very meaningful level of security. And so, for example, here you're only going to leak the fact that you have plain text equality, which is something that randomization requires to get rid of that leak. And then if the randomness is predictable, then we'll, again, get a slightly degraded security level, but still very strong. And here that only plain text equality gets leaked, assuming that there's sufficient entropy in your message randomness pair combined. So let me just talk briefly about this last case, which is in some sense the hardest for public key encryption. And if we sit back and think for a second about our encryption mechanism, well, there actually always exists an attack against public key encryption. And it's just a brute force attack that works as follows, right? You enumerate the set of all possible messages and the set of all possible R values. And then you just iterate doing trial encryptions over each pair. And then check to see if the output ciphertext is equal to a target one that you're given. And if it is, then you know what the message of that target ciphertext is. OK, so this always exists, but it's not always practical. So of course, if the set of messages or the set of randomness is very large, then this is inefficient and is not going to be tractable in practice. And so at a very high level, what our target for hedged public key encryption is that security, a secure hedged public key encryption scheme basically mandates that this attack is in some sense the best attack possible, that any other attack will essentially work only as well as this brute force attack. So how can we achieve such a thing? Well, we had this idea that if we could design our encryption scheme to behave like what's called a randomness extractor, then we would actually achieve this goal. So randomness extractors are these classic objects that have been used quite extensively in computational complexity. They're used in contexts like de-randomization of randomized algorithms and been studied extensively. What do they do? Well, they're a map that uses a seed S to map values from some large domain to a smaller range, but with special properties. So for example, if you choose any subset of the domain that's smaller but of still large size, then any point chosen randomly from this subset actually gets mapped to a uniform point in the range. And so in particular, if we just have our encryption mechanism actually act as an extractor, so we choose our public key to be such a seed, then this properties of the extractor basically makes it look like if you have a message randomness chosen randomly from some set of MRs, then an output ciphertext given to an adversary is just going to look like a randomly chosen ciphertext. And so you actually hide information about the message. So this approach has a critical failing, which is that we need to be able to decrypt messages. And extractors are fundamentally compressing objects. To get these properties, you need to go from a large space down to a smaller space. So you're throwing away some of the information you would need to decrypt. So we can circumvent this, actually, using some new cryptographic objects called universal lossy trapdoor functions. And the idea is actually, at a high level, somewhat simple. We have a function now that actually there's two different types of keys. So you can choose a normal key, pk, which has a trapdoor associated to it and actually maps to a set of a range of sufficient size so you can decrypt properly. But at the same time, there exists another way of generating a key, S, such that the encryption algorithm now works like an extractor. And so what it does is actually it only uses some relatively small subset of the entire range to map values from D2. And moreover, the point is that these public key and S values are indistinguishable. So from an attacker's point of view, if he's given the encryption of a MR and another value, either the PK or S, he can't distinguish between the two. So it might as well have been encrypted with this extractor key S. And so that means that we get back to this place where we get the nice properties from extractors that they're hiding information about sufficiently high min-entropy inputs. Yes?
Okay, yeah. Can you give an intuition for the non-graphic way?
Say again?
Can you give us an intuition for those of us not steep?
Okay, so at a high level, what's the motivation here? That we want to take advantage of any entropy in the message space to make up for a lack of entropy in the randomness. And so we'd like to basically take advantage of all entropy in the MR, in the message and the randomness combined, and extract that out fully. And so what extractors have been used in other cases where you basically have some set of measured events, right? These are actually used in some sense for random number generation. And what they do is they take any inputs and they map it to an output, and it looks like a uniform point. Okay? But the fact is, to do that, to get that property, you need to have a smaller set. And so that comes the cryptographic component. That's actually design a functional encryption scheme. We need to do something more clever. And that's where this notion of LTDFs comes in, these lossy trapdoor functions, because they have two operating modes. When you actually use it in practice, you use a public key that actually maps to a set that's big enough to decrypt from. Okay? But when you're doing your security proof, you can then say, well, from an adversary's point of view, you can just imagine that this public key behaves like an extractor. And it gets this property that the output just looks like a random point.
Why is that valid during the security proof? Why can you say that?
Why can, well, I mean, there's a lot of details, but.
From any other cipher.
I'm sorry, say again?
Why does the security property continue to hold? You've proven the security property when you're using it in one mode, when you're using it in this reducing mode.
So the point is
actually applying it in a different mode.
Right. So the key thing is this last kind of mumbo jumbo at the bottom, which is that from if I hand you a ciphertext and a key, let's call it D or something, and now D is either a public key or an S, and you can't tell the difference. So in the proof, we take advantage of that fact to say, okay, if we're encrypting a message in regular world with public key, you get a ciphertext. It might as well, from an adversary's point of view, been encrypted with this value S.
You say it might as well. I mean, in practice, the adversary can reasonably assume that if
Right.
you're actually using this in practice, it really is a real public key.
Right. But the point is that if you can distinguish between, if you can learn something about M, then you're going to violate, we can show using these reductions that you're violating the fact that these two things are indistinguishable, which we've proven under some complexity assumption like, well, not factoring, because we haven't shown that relation here, but something like solving discrete logs or CDH or DDH, I guess in this case, decisional to Hellman. So the point is, if in the proof, if you show this, what you've shown is that any attacker that does learn a message about M is actually able to do something hard. And that's what the proof is ended up showing. I was just giving you intuition about one of the steps of the proof and trying to gloss over quickly. Okay, so there's proof stuff, and then the fact is that we can take these ideas basically. Oh, good, and we moved. And moving from the starting point, this is actually, these constructions are not practical. But what we showed is that we actually can do a practical framework for hedging a variety of randomized primitives. I won't talk about it, but the fact is you can just go and implement it, and it's incrementally deployable. It's backwards compatible. Yes?
What efficiency do you get compared to, say, RSA?
So in the end, it's like doing 2 more HMAC calls over RSA by itself. Or an RSA-based encryption scheme.
Identical, in other words.
Right, yeah. Mm-hmm. Mm-hmm. Yeah, not the construction we were showing, but there's a simpler, less mathematically interesting construction, but something that's very practically interesting. Yeah. And so we implemented it in the OpenSSL library. And the takeaway is that now what we get is that we have implementations of the cryptographic tools that provide us nice defense in depth, right? Graceful degradation of security in the face of bad randomness, right? So if some randomness failure occurs, our crypto operations are no longer going to just fall over completely, but give you this graceful degradation of security. Okay, so we saw in the last 2 examples, right, problems where we identify some issue of practical concern and dealt with it by modifying the crypto. Okay, and in the next example, which is kind of systems building example, we're going to see is that while we can do a bunch of machinations and design with cryptography, we're going to see that this doesn't actually solve the whole problem. And so here it's going to become important to understand the role of the crypto in a broader system security context. And this context is device tracking. So let me tell you a bit about device tracking systems. The idea is straightforward, right? You install on your mobile computing device a tracking client, which is going to use the internet to update a remote storage service operated by some third party about the current whereabouts of your device. This could be the time, the IP address, what wireless network you're connected to, and maybe other forensic data like pictures taken with a webcam. And then the idea is that if it goes missing or is stolen, the tracking client should nevertheless keep updating the storage service with this data. And the user, can retrieve this data, work with the authorities, and try to attempt recovery of the device. It's exactly like LoJack, yes. Boom. So LoJack is a great example of this. And And the point is that there's actually a big industry surrounding these products now, and there's a lot of companies offering them, and they're all competing on this engineering to ensure that tracking succeeds in the face of physical adversaries, right? So this laptop has a LoJack client actually in its BIOS, for example, to survive hard disk formats and that type of thing. We were interested in a different aspect of this problem, which is the privacy issue, right? That, of course, that these tracking services are also, as designed, tracking the legitimate owner via their devices. And so from a psychological acceptability standpoint, this seems a bit uncomfortable. And so we pose this question that can we provide a tracking service that, at least the tracking service, provides the functionality that's required in the sense of tracking the system after it goes missing, but at the same time protects the privacy of the owner when it's in their hands. And so, of course, the first idea we had was that we'd like to just encrypt this content before sending it over to protect it from people at the remote storage site that's being operated by other parties. And so we can do that, but there's two problems with this. One is that, of course, other users are going to be making use of this remote storage service. And so there's going to be a big database of anonymized encrypted content. And so the question is, how do you actually efficiently retrieve a particular user's updates if, by definition, you want this stuff to be anonymous? So we can actually solve that using some fancier cryptography, but I'm not going to talk about it because I talked a lot about crypto. I'll just put up this kind of scary-looking flowchart. But the idea is that you want to provide mechanisms that provide fast search over encrypted data, and so allow the user to retrieve his data efficiently without revealing information about past locations. There's a second problem here, which is that, okay, even if you do all this fancy stuff, the fact is that when you're talking over the internet, you're revealing your IP address to the remote storage service. And yes, is there a question? Half question.
We said there were two problems. Isn't there a third problem that once the bad guy gets your device, he also has your encryption keys and can say,
right.
I lost my device. I wonder who had it in the past.
That's a great question. Yeah. So all the fancy crypto is providing forward privacy. So as the device uses up encryption keys, it basically picks new ones in a deterministic fashion, but such that you can't recover previous keys. You can think of that. Yeah. It's like AES. Yeah. Mm-hmm. It gets a little bit complicated because we want to build in things like a cache on the site so that you can cache the last few locations inside the client. So you have to encrypt this and kind of re-randomize encryptions before sending them off and this type of thing. But yeah, we dealt with that issue. Mm-hmm.
I'm a little confused by the model. Is it assumed that I don't have some home trusted store that I can keep? Because if I do, then...
Right, you want to take advantage of a third-party service to provide the storage of your...
Storage, yes. But if I, at home, could just store a key, or sort of match the forward secrecy key that's going on, then I just encrypt with that key from the device, and the third party can't read it, and nobody else can read it.
When you say home, do you mean on your laptop? Because I'm here right now, and my laptop is updating some...
No, I mean I have some...
A floppy disk.
Yeah.
It's called a USB.
So a floppy disk? I don't have any floppy disk. So I'm confused about the question. I'm sorry.
I have, in a safe in my house, a small amount of data. Basically.
Yes, that's the exact idea, yeah. So we're going to initialize the client with some small, like an AES key, and that's going to be used to deterministically generate more material that we use to encrypt and index our updates. The client needs access to those values and needs to send them off.
Yeah.
Okay, and that's the intuition behind the cryptographic component.
But the anonymization doesn't seem like a big issue at this point. Then just everything I'm saying to the third-party service is already encrypted, and the third-party service can't.
Right, so that brings me to the next point. Why is this point that you're revealing IP address is potentially damaging? And the idea is that there's partial information leakage here that you can do based on traffic analysis, right? So, okay, we send an update now that it's totally anonymous and encrypted from a particular IP address at a particular time, and we're sending it to a remote storage service. And so this is what the remote storage service sees. Now, what you can do is take this IP address, and this already reveals the location, right? Because you can use a geolocation service to identify where the IP address is physically in the world. And so, okay, now you know it's a home residence, right? And so the point is, next time you see an update from this home residence, you have a good guess that that person now returned to it, for example. And so while it's not 100% damaging, like you're not revealing everything all the time, and you can hide to some extent in crowds, the fact is there is partial information being leaked about locations via just the fact that you have an IP address. And so we set out to try and to solve this issue as well, right? We don't want to just rely on the crypto. There's a systems security issue here. And so can we deal with this, mitigate this threat of traffic analysis even beyond what the crypto can provide? Okay, so there's actually a long literature on inhibiting traffic analysis, which revolves around doing onion routing. So the idea is you just bounce your packets off a distributed, randomly chosen set of nodes to kind of launder the source IP address. And so we could use this type of system as well. But we thought, well, maybe we should. We actually thought, okay, there's overheads with these types of things, like latency and code complexity and such. And the question was, so we were motivated to say, can we actually improve privacy from traffic analysis in some sense for free by using some decentralized storage infrastructure to store updates? And so the idea is we ended up using what are called distributed hash tables. Now, these are systems that are decentralized. So you have something like Vuz or Azurius, which has millions of nodes in it, and it's being used for things like BitTorrent. And it provides a very simple API that you can put data under some index and then retrieve later that data by providing an index. And so what we ended up doing is saying, OK, let's take advantage of this decentralized architecture. So when we do all this cryptographic work, we also pick cryptographically random indices, ones that can be recomputed later by the owner. But from an adversary's point of view, without the original key, they just look like random values. And then when we do a put, we do a put under using that random index. And what this does is actually ends up choosing a random node to talk to in the architecture. And so the next time you do an update, it actually chooses another node. And the idea is that now we've diluted trust across this decentralized storage infrastructure for free without having to use onion routing. And so even if some subset of the nodes are compromised, they only see one if that many updates is the idea. Okay, so with privacy systems, of course, we were interested in seeing, is this actually deployable? Could people use this type of setup, both from the cryptographic side and with DHTs? And so we went ahead and implemented and released a tool. These pictures were taken from our client. We had a lot of fun playing around with the webcam there. And we were very happy with the results, that quite a few people downloaded it and have been using it. And then maybe more importantly, this idea of using DHTs as a security privacy tool picked up a bit of steam, and there's been follow-up work in the community about the efficacy, this idea of using DHTs. So, okay.
Those participants actually run OpenDHT clients?
No, they took advantage of the existing OpenDHT architecture, yeah. So most of the clients. So OpenDHT might not be the best realization of this, but we used it because it was simplest to work with. And it has, I think at the time, it had something like 160, 170 nodes. So from that point of view, yeah, you may end up talking to all the nodes at some point over the lifetime of the client. You're still achieving some benefits in terms of privacy, but it's not going to be to the scale of like if you linked in with Vuz or Azurius, where you have millions of nodes. But we wanted to use OpenDHT because it was simplest to work with at the time, and as a prototype to see if people would actually be able to use and would want to use this.
So the property you get with this is that if there are compromised nodes in the DHT, which are pretty easy to create,
right?
Because you can symbol a packet if you really wanted to.
Right.
That, I'm asking if I understand this correctly, that you would get to see information about some IP addresses that we're sending in things, but it would be randomly selected from among the whole set. So, right, you get good information, but you wouldn't be able to target it. Is that what's happening?
Right. So some portion of the updates are going to miss the compromised hosts, right, from a particular client. Most of them, yeah, that's the idea. So if you had a Sybil attack where you took over the whole DHT, then you're back to the fact that you have encrypted and anonymized all the updates, so you have a little bit of privacy leakage, but not that much. If you have a DHT that resists Sybil attacks, you get much stronger privacy improvement against for these particular traffic side channel attacks. Yeah, that's the idea.
But if you did onion routing,
you get
stronger property.
Right, and then onion routing, of course, has its own issues about whether it's secure all the time or not. But right, so you could do both, right? You could route the DHT puts across onion routes, and then you would get like the most paranoid level of privacy ever or something, assuming all the components are good.
Although to some extent, you only need to be private up to the point that it's easier for somebody to just stick a webcam outside your house and see you walk in.
Right, exactly. And that raises a good point. That there's plenty of other ways that location privacy can be violated by someone's laptop, right? Even. So if you contact Gmail every time you sit down with your laptop, of course, you're notifying Google of all the locations you're visiting. But solving the location privacy in the global sense is a much more, and at the moment, intractable problem. So we were trying to say, just for the device tracking component, can you ensure that we're not doing anything?
Does onion routing really help here? Because if the first node you touch is compromised, you're screwed either way, aren't you?
But you choose a different node each time, so you get the same type of guarantee you get from the DHT that we were using.
Yeah, but I don't think onion routing adds anything.
You're right, Josh, that's an actual.
Well, there's another layer of potential. Yeah, I mean, yeah, that's actually a great point. So if you're, yeah, you get the same level of guarantees.
Well,
Yeah,
it's
that's
a
good.
little bit better because in the DHT routing, you actually have to take multiple hops to the DHT to see it.
Yeah, there's a lot of details I'm glossing over with the DHTs
But that's like a factor of one.
For example, we have to do replication as well to get functionality of the DHT. So you actually, it's not just one node you talk to 3, and then if you actually have to communicate with multiple nodes for each put, then you are leaking more. So there's a bunch of details there.
Is this less complex than Tor? Because the other reason you gave for superiority over onion routing was latency, which I can't imagine is an issue here.
Well, so yeah, it may not be an issue, a killer issue, right? One thing, to be perfectly frank, is it's easier to work with OpenDHT when we're implementing it than to work with Tor, right? It's a big code base. We want to have a very small client to fit in something like a BIOS at some point. The latency issues, I mean, you have to complete this circuit, right? So, yeah, in general, it may not be a killer issue, but the idea is we wanted to experiment with this DHT and get it for free, and then you don't have to have Tor and rely on other people's Tor nodes and all the security issues there. So, in the end, it's going to be a choice for deployment, right? If you want to use both or one or the other, it's up to the people who end up designing the system.
But Tor is even heavyweight for onion routing here, because you really just need to send one packet in one direction. You don't really need to establish.
Right. So you could use a mix router or something.
Tracking
Yeah.
here is offline.
If there was a latency
in band with the communication.
I'm sorry, say again?
So, but here the location tracking with OpenDHT is offline of your communication.
Right. I mean, you still need a remote storage service either way, I guess. I'm not understanding your question. But let me move on. I have a whole other topic I wanted to cover. We can take more questions at the end. So let me just get into it in the interest of time. And this work was about cloud computing security. And of course, cloud computing is going to be quite the consumer of cryptographic services. It already is. So we're interested in what types of threats exist in this context, and whether there's really new threats that come up here, or if there's kind of the same old issues. So what is a cloud computing service? Well, we were focusing on so-called infrastructure as a service systems. You have a provider that has a bunch of physical hosts with a virtualization layer running on top of it. Users can come and pay the provider to run their computational tasks in the sense of running virtual machines on their service. They're quite dynamic, so you can start and stop virtual machines at will, start them up again. And an important facet and feature of these types of clouds is the use of multi-tenancy. That, simply put, users are sharing physical resources. And of course, this is important from the provider's point of view, because then they can statistically multiplex their physical resources across a wide user base and get economies of scale that way. So again, this is powered by virtualization. So each physical server has a virtual machine, a hypervisor, a virtual machine manager, a hypervisor running on it. And the idea is that this should provide the appearance of having a dedicated machine to oneself. So we're interested in the following hypothetical threat that lies at the intersection of this use of multi-tenancy with the fact that these clouds are public, that anyone can start running virtual machines on them. And so the idea is the following. That an attacker is going to identify one or more victims running in the cloud, and then try to exploit what we call a placement vulnerability. So for example, the attacker could launch lots of virtual machines and have each of these check somehow for co-residence on the same server as the victim. And should this be successful now, the attacker can mount attacks to take advantage of this close physical proximity. So you could, of course, exploit some known VMM vulnerability and then just take over the whole box and kind of have a targeted way to use a known vulnerability. You could also do denial of service attacks, so degrade, use up resources trying to degrade the efficiency of the victim. And then the perhaps most subtle threat would be that of physical side channel attacks, which is that just the fact that you're sharing the same physical resources, cache, memory, hard disks, might be sufficient already to extract some confidential information out of the victim. So this is a hypothetical threat. We were curious to see if it's actually a real threat. So we did a case study with Amazon's EC2 service. And what we were able to do, despite being white hat researchers and abiding by the acceptable use policy of Amazon service, we were nevertheless able to do the following. Engage in what we call cloud cartography. So this is mapping out some, if not all, of the internal infrastructure of the service. With particular end being that given a target, a public IP address, we can locate approximately where in the infrastructure this target is running. And in particular, identify launch parameters that would be advantageous for malicious virtual machines to be ran under to try and end up on the same physical server as the victim. Learn how to do co-residence checking, so actually understanding when you're successfully on the same physical server. And then we did measurements to experimental measurements to see if this is frequently achievable, and it is. And so the problem is that, of course, this already reveals a placement vulnerability that attackers can knowingly achieve co-resonance with a victim. This is dangerous for a bunch of reasons. We were particularly interested in this aspect of physical side channel attacks. And we're able to show cross-VM side channel attacks that can spy on the momentary computational load of a victim. So I'll talk about each of this in a bit more detail now. But first, let me give a very high-level overview of some of the instance networking of EC2. So you have virtual machines running within a Zen virtual machine manager. Each virtual machine has associated to it an external IP address and an internal IP address. Conveniently, from an attacker's point of view, the internal DNS service in EC2 actually maps an external IP address queried to it by any party to the internal IP address associated to it. And this is, I think, is to encourage people to communicate via internal IP addresses within the cloud. They priced differently, and it's more efficient for Amazon, presumably. Our experiments indicated that the internal IP addresses are statically assigned to physical servers. So each machine, for example, hosting the smaller type of instances ends up having 8 contiguous internal IP addresses associated to it. And in fact, the way they did their networking actually provided, in hindsight, a very simple way of doing co-residence checking. We did a lot of work to establish that this works, but in the end, it's simple. You can just do a trace route to a target internal IP address or public IP address, and if you only have one hop, then you know you're on the same box, because what happens is the VMM actually routes the traffic right back to the guest operating system. So with that in mind, we know how to do co-residence checking, but how do we actually kind of figure out where in the cloud a victim is, and how can we understand how to get to that portion of the cloud? So what we did is this measurement study that we call cloud cartography. So we identified a bunch of launch parameters for virtual machines in the EC2 service. So for example, this includes things like the availability zone, which are advertised as disjoint portions of the internal infrastructure for redundancy purposes, the type of virtual machine instance requested, and there's just a varying levels of virtualized resources that are handed to the virtual machine. And then, of course, things like the user account are also identified. So what we did is run, using an account under our control, virtual machines and changed each of these parameters one at a time. So here we have a graph of the internal IP addresses of the resulting virtual machine instances colored by the requested availability zone. And so what this shows is that the internal IP space is segregated according to availability zone, which makes sense in light of what they're advertising availability zones to be used for. Can repeat this for instance types. Here we have a bunch of virtual machines that we ran that are colored by the instance type. And again, we see quite a bit of regularity in terms of which portions of the internal IP address space are being used by which types of instance. And then this bottom half of the chart is using a second account. And we end up in the same portions of the internal IP address space. And in fact, ended up with the same internal IP address many times. So we can take this idea kind of to the logical conclusion and basically provide a map now that associates, for example, to each /24, so the first 3 octets of an internal IP address, an estimate of the availability zone and instance type that we think are running on that chunk of IP addresses. And so this proves quite useful because then given a set of public IP addresses, for example, we can map all those to internal IP addresses using the internal EC2 DNS, and then just look at the first 3 octets to get an estimate of the availability zone and instance type. And this is just a chart showing colorings of a bunch of public HTTP servers that were running at the time of the study, with the point being that we get quite a good coverage across the internal IP address space. So, OK, so now we know how to locate approximately in the cloud where a victim is, and we know specifically what launch parameters would be good for us to use. And so now that we've kind of narrowed the search down, can we actually get on the same physical server with good frequency? And so we did a bunch of different experiments to assess the likelihood of this. And I'll just tell you about one of them. And the setting here is that we are able to launch the attack virtual machines relatively near in time to when the victim was launched. And so we did an experiment where you launch a target virtual machine, and then you launch from another account a few minutes later just 20 quote-unquote attack virtual machines. And all these did was check to see if they're co-resident with the target. And so out of 10 trials, this already succeeds 40% of the time. So immediately you end up on the same physical server as the victim. And this is actually very cheap. At the time it was $2 US. I think it's gone down since then.
You say you launched them from a different account. Did you launch them from the same client?
I'm
In
sorry.
other words, the same
IP address?
Yes.
For these experiments, no, I changed between different IP addresses. I mean, it was from the same UC San Diego domain, so they could be. We didn't exhaustively experiment. I also did some launches from home. It seems that they're not taking that into account. Of course, they could, but my sense is that they're not. And of course, there are some portions of the EC2 infrastructure that we don't have access to. I mean, they have large corporate clients that maybe get some portion privately. But for this kind of public portion of the cloud, it seems that you can really get on the same systems. I mean, we did use, for example, there's some free demos from some companies that use EC2 service. So they had like, they call them cloud appliances or something. And you can launch a free demo using their web interface under so it's their account. And we were able to achieve co-residence with those as well. OK, so what can you do once you end up on the same physical server? Well, we experimented with this idea of physical side channel attacks. In particular, showed how to do a cross-VM load measurement using CPU cache contention. So the idea at a high level is straightforward. You have an attacker and a victim virtual machine on the same CPU architecture. And so what the attacker does is first read in a large array of data to basically ensure that he uses the entire CPU cache. And then the attacker idle loops with the idea that this will allow the victim to run, hopefully on the same cache architecture. And if the victim has computational load, it's going to use up some portion of the cache for its own purposes. And so when the attacker runs again, he can now measure the time to read in this large array, and this becomes the load measurement. And the point is that it's going to be correlated quite strongly with the amount of cache usage by the victim, and consequently the amount of CPU load that the victim is currently under.
So what's your intuition about how fine-grained these side channel attacks might get and how hard it would be to defend? I mean, are we worried about private keys disappearing, or are we worried about really coarse stuff? Because load I can infer by just poking at the victim's HTTP server and seeing how latent it is anyway. And so the question is, how scary is this threat? I mean, if we poke at this for another 10 years, are we going to be getting private keys? Or okay.
So yeah, my sense is that I don't know, and I think in general, there needs to be a lot more research on these side channel attacks. Basically, they're all kind of a black art at this point. You have someone sit down, some grad student who has not enough free time on their hands, and figures out how to do an attack for a particular architecture in a particular setting. And the granularity there is basically depends on a lot of different factors: how many cores you're floating between, how much noise is on the system. And we don't really have good tools, as far as I can tell, of quantifying this type of attacks. And I think that's a great open research question. The concern, of course, which I'll talk about, is that these attacks that we used are based on the side channels that in non-virtualized settings, we're able to extract AES keys across process boundaries in certain settings. So there's looming concern that, yeah, as you get more refined attacks, then you're going to be pulling out more and more dangerous confidential information. AES may not be a huge threat in the future because we'll have an AES architectural chip for, on Intel architecture, we'll have an AES instruction. But the problem is side channels are difficult to close down. Mm-hmm.
It seems like you got to separate the world into two problems. There's the getting information from particular VM host that I'm interested in getting information from, and then there's the how I actually get information. Side channel attacks are probably very hard to defend, will always be there.
Right.
But this ability to target, I mean, do you think that this is important? I mean, Amazon's placement algorithms were optimized for bin packing, for efficiency, and they have a relatively small cluster. So in the same way that you used to be able to inject information into TCP streams because we used predictable sequence numbers, we decided that was a bad idea. We started to randomize. I mean, aren't we just going to make this co-residency impossible in the future?
So the fact is, if you're doing multi-tenancy, co-residency is not impossible, right? If you're sharing physical servers between mutually untrusted parties.
Yeah, but I can make it arbitrarily.
Can you make it arbitrarily? I think it's an interesting question.
Arbitrarily difficult to
so certainly. Yeah, sorry. Finish your.
Yeah, can I make it arbitrarily difficult to achieve co-residency with a particular target?
You can make it arbitrarily difficult if you don't allow someone else to get on that box. I mean, so there is one way to make it impossible, which is to shut down multi-tenancy, right? Which is actually something we suggest as the only surefire solution here. I think if you allow multi-tenancy, the question is, can you make it arbitrarily hard? I don't know. It's a good research question. I think you could close down a lot of the things that we took advantage of, like network configuration issues, right? But that's only going to slow an attacker down, right? So it's a good question. I don't know. Whenever you have multi-tenancy, you have the potential for getting on the same box, and you have side channels. So it's something we need to think about. And the point of the research was saying, look, that there is this new aspect in cloud computing, right, where you have this first step. You have to get onto the box first before you can take advantage of close physical proximity. And so is this something that's realizable? Well, it turns out yes. Can we defend against it? It's an open research question. Yeah. OK, so applications across VM load measurement. So we can do things like measure relative traffic rates across virtualization boundaries. So for example, we set up an Apache server and an attack VM that was co-resident running EC2. And then we just varied the level of traffic sent to the blue server here. And the bar chart on the right reveals the load measurements that were taken by the attacker. And so we see the strict differentiation of load measurement. And so information is certainly leaking here across boundaries. Yep.
What do you mean by load here? Because load is clearly not CPU load.
I mean in an abstract sense. So load measurement here is the read time from that third step in the algorithm. And so it could be a bunch of different features. But the point is that you can correlate it to other things that are happening with the box, right?
You can correlate what? I'm not understanding what the it is.
Correlate what? So here it's the relative traffic rates, right? So you know that if you saw in this granted experimental setting, right? You see higher levels of load measurements. You know that there's more activity going on, more HTTP requests occurring.
Stuart's asking what the units are.
Oh.
Right, because it looks like
units?
so.
Oh, this is the mean CPU cycle.
Load the array.
Right.
Okay, but this happens
to load the array in the third step.
This happens to be a metric where you're going to have a strong correlation between memory use and CPU use. Because your CPU's
I see what you're saying. Yeah, but so right.
From memory. So this doesn't seem like the right. It seems like if you're only using this test, you're getting the wrong. You're measuring the wrong thing.
For what exactly? So for some applications, yeah, maybe you're not hitting the cache as much, and then you won't get any signal, even though you have CPU
you can
load.
Put
right.
Lots of cryptographic load on. It's not going to touch the cache too much.
Well, that's the exact problem that like AES does use the cache, right? And so. That's where we get issues with AES side channel attacks across process boundaries, which could end up being a problem here. So, I mean, you do use the cache for lots of different things. The question is, maybe there are some things that are literally only in registers on the CPU proper and not using the L1 cache or the L2 cache at all, and then you wouldn't be able to measure those type of behaviors. You're right. So it's a cache load measurement, I guess, would be.
Measure that by just counting what fraction of the time you're actually sitting in your busy loop. I mean, see how much just look at how much you get scheduled. So
it is yeah. So you'll see that if other instances are busy, for example, you'll get floated more frequently between cores and stuff. So these are other ways that information is leaking across. But that doesn't take advantage of the cache. I mean, the point, yeah. I mean, this is just one example where we said, okay, here's a proof of concept in EC2. We can get information leaked across virtualization boundaries, right? We can get on the same box, and then we can do it. Now, maybe this isn't the most damaging thing to be learning in the first place, but it's something you shouldn't be learning. The virtualization is supposed to be stopping this type of leakage, or at least that's the concern, that people think that this is the case. And so, in general, there's going to be a whole wide range of side channels that you might be able to take advantage of. We also looked at, taking care of memory contention, hard disk contention. Of course, I was talking to someone about network card contention, and they were saying, oh yeah, this seems like a great way to get in a good position to take advantage of network card contention to identify encrypted streams and these types of things. So so there's a lot of different ways you kind of play as an attacker with various shared resources once you're on the box. I mean, you still look confused, but maybe we can talk about it later. We're running low on time.
Yes.
Yeah. Okay, so we show other things, EC2-like setting, key press timing. You could kind of do this and get even finer grained information. Of course, the future work the concern is about AES cryptographic keys or other cryptographic keys being taken across virtual machines. We think this is a big problem. Talking to people at certain companies and others, they seem to agree that this is an issue that people should be concerned about. There's a lot of potential countermeasures we could look at, but this is an open research question about what are the trade-offs and whether you can even quantifiably come up with any resistance to side channel attacks. It's an open problem. Let me just finish off very quickly with saying a bit about my future work, and I think. I've cast cloud computing stuff in a negative light in the last bunch of slides, but actually the project made me quite excited about cloud computing in general. That really looking forward, we can kind of see that this is going to take off. It has a lot of value added for customers, and we're going to end up in a world where a lot of computation tasks, if not the majority, are going to end up being done with clouds. In some sense, we're going forward, but we're also going backwards. We had long ago many-to-one systems where you had shared mainframes with many users sharing one single computer. Then we had this personal computing revolution with kind of one-to-one mapping. And now with cloud computing, we have this now many users sharing heterogeneous distributed infrastructure, say this many-to-many mapping. And with this change, we have a lot of security challenges looming. We identified one, but there's others, and I want to understand these. So for example, I think investigating more how the mismatch of our legacy abstraction, so how engineers have been designing software now for the one-to-one personal computing era, really have mismatches with the current realities of running these things in cloud computing settings, and understanding if this is going to give rise to further security vulnerabilities. I think another interesting line of work is about understanding whether we can do cryptographic auditing of cloud services. So the idea is that right now, cloud services are quite opaque from a user's point of view, and they want to have guarantees about their data and their services. And so can we even provide technical mechanisms that could complement any contractual mechanisms to audit, for example, that a cloud is truly using enough redundancy for our data, for example. And then finally, and a bit farther out there, I think that we saw with the move from many-to-one to one-to-one personal computing, we had this kind of revolution in electronic crime. And I think it's interesting to at least start thinking about what type of repercussions moving to this new setting is going to have on the underground economies that are going out there. Whether we can get ahead of this is one question, but also just understanding and measuring electronic crime is a considerable challenge and something I think is fascinating.
Changes in crime were motivated by the computing model switching from mainframes to personal computers, or just by the fact that it got a whole lot bigger, and so there's a lot more opportunity?
From a crime point of view, I guess it doesn't really matter exactly what the motivation was. The point was that having one-to-one personal computing kind of enabled this new wave of crime, right? Yeah, so in some sense it's from more people using it, but then we'll see a similar explosion that more people will be using a variety of new services because of cloud computing. And so similar effects might be going on. Lastly, before I finish, just want to thank, of course, all my collaborators. Without them, this work wouldn't have been possible. And at this point, I guess I'll just take questions. Thank you.
I think we already asked lots of questions.
Yeah.
Thank you.
Thank you very much.